a great pleasure. It's a great pleasure to talk, and I've seen the program, and I wish I had noticed the series earlier because we had a few really interesting speakers, so it's a great honor to speak among them. I also spotted in the audience a lot of old friends and who remember some of these times, the times I'm going to talk about from when we were all in Hamburg. So this is another fun aspect. Some of what I'm talking about, I snitched some slides from Peter Stott from a talk we made together a while ago, and and also a lot of colleagues were involved in the work I'm talking about, and I'm acknowledging them here, and also my long-term postdoc and now a fellow colleague in the University of Edinburgh, Andrew Schurer, and also of course Simon Ted. So, and it's not moving forward slides. Oh, it is. So the question of the detection and attribution of climate change is basically about connecting the observed increase in CO2 with observed changes in temperature. That was the key motivation of raising the question: is the observed warming linked to CO2? But of course, once you raise that question, you also get into many further questions, for example, involving what have aerosols done as opposed to CO2, and what is the role of natural influences. So, so we need to look at a variety of external influences on climate and on climate variability as well. And the aspect that you couldn't see from these time series is also that, of course, there are spatial patterns. And it has been, if you even if you don't know the literature, it's been quite striking, for example, how the observed warming that's been shown in the IPCC AR5 report at the bottom left resembles in pattern the projected warming into the future. So that is quite a striking comparison. So the spatial pattern is something that's going to play a role in what I'm going to speak about as well. Why would you even want to know? So there have been some people said we know anyway from physics that this has to there has to be a link, but the question arose from, I think, several angles. One thing to think about if you try to look at if the observations contain a greenhouse gas influence is that we know that we know, of course, from Planck's law that if you increase greenhouse gases, then you change the radiative budget of the planet, and you have to have a response in temperature to address this imbalance if you retain more outgoing radiation. So you could argue that we know from physics that CO2 increase has to raise climate change, has to change climate. But on the other hand, the exact magnitude of the response is dominated by uncertain feedbacks, particularly those involving clouds, and what is exactly the climate sensitivity is an ongoing long-term debate. That this problem of attributing climate change to causes plays into as well. And so you could hypothesize, and some particularly skeptical voices have done that the feedbacks are all negative and making this whole response weaker. And so it's a non-issue. And while there might be a response, it's not large. That, I think that already tells you that the question should not have been, is CO2 changing climate, but how large is that change? And it took the community a while to realize that that's actually a better question. And so the first test, therefore, but still the first test to check is the observed change indeed caused by human influences, or if have other factors been driving it. So even if the question really is how large is the human influence, and not so much is there a human influence, you could also argue the question, is there a human influence, is the human influence comparable in size to natural variability? And then lastly, results from detection attribution, results that have used the observations to estimate the response to greenhouse gases, can be directly used to constrain future climate change. It works, and I'm not going to talk much about that in this talk, but it works basically like this. If your analysis shows you that the observations support a weaker change than observed right now, or a stronger change, and the enhancement or reduction factor should be a value you've estimated from observations. You could use that to constrain future climate change. And actually, the IPCC 4th and 5th assessment report have used this. So they have not only used the model projections, but have also looked at the observed estimated greenhouse gas response and have used it as a further line of evidence to estimate the future and likely future warming rate. So it's a usable and useful information for projections as well. So hopefully I've now motivated you that this is a good question. And when you start to want to ask this question, to what extent did greenhouse gases warm the planet, you have to immediately worry and think about other effects on climate that you need to distinguish from. And one of them is natural forcing. So we have on the top the solar irradiance changes, and you can see the variations in the solar irradiance from satellite data is quite an interesting quite distinct 11-year cycle, but you can see by eye that it's not a totally regular cycle, and that, for example, there was a lot of excitement in 2010 when the solar cycle didn't seem to come back, and a lot of hypotheses that we might be going into a grand minimum or something, which hasn't happened. So you have a relatively regular 11-year cycle and some unknown and hard to estimate low frequency variability in the sun, and then you have volcanic eruptions, which this figure we will get back to shows up quite nicely. So where you can see in the observed in black and model simulated in red simulations of climate change, you can see the big volcanoes, Agung, El Chichon, and Pinatubo, causing visual dents in observations and the models. And it's due to the aerosol layers, of course, in the Earth's atmosphere that are here seen from the space shuttle. And we have also aerosols, and that the complication by aerosols has been recognized relatively early. This is a picture from 2001, but a lot of the early papers I'm going to talk to you about include aerosols as a possible complication quite early on. So aerosols reflect and some of them absorb, and they have a tendency to be very poorly constrained. So we of course can measure the aerosol optical depth from space, but it's very hard to see how exactly they influence clouds. So they're a big uncertain factor in terms of both pattern in time and space. The pattern in time is interesting because the aerosols have been reducing with pollution control measures in Europe and North America in the last few decades, but are still increasing in East Asia. And so you have a globally flat, but regionally quite distinct change in the recent period. And then, of course, the really interesting complicating factor is climate variability. And so this is from old models and from the AR4. I think a power spectral comparison that both in all the models and in the observations, you have a red noise power spectrum due to internal climate variability, and it expresses itself in weather variability, but also in its lower frequency components. So, and I'm going to get back to the red noise in a second. So the whole problem got kick-started when Jim Hansen declared in a Senate meeting, in a Senate hearing in 1988, that he was 99% certain that the Earth was warmer than it had ever been measured to be, and there was a clear cause and effect relationship. So that, I think, took a lot of people by surprise a bit, and there were a lot of there was, even at the time and for a long time after, I remember when I started at Max Planck Institute, there was debate that this really he really didn't have much foot to stand on. His intuition was right, of course, but I think science isn't about intuition, and is about actually demonstrating this. And of course, he wasn't the first to think about the influence of greenhouse gases on climate. There had been much earlier discussions that the CO2 fluctuations could have a role in ice ages, and also Callendar was, for example, hypothesizing that the early 20th century warming was caused in parts by the greenhouse gas increases. So, but that brought this question to the question that if greenhouse gases cause warming and how much, very much more into conscience. And this, I think it's not an accident that the IPCC was founded in the same year. But there had also been some thoughts about how could we detect climate change and how could we be actually certain that what we see in observations is due to greenhouse gases. And Klaus Hasselmann, whom I think many of us in the audience remember, and we are looking forward to his 90th birthday soon, had written several important papers about the question. And not by accident, I would like to first start with the stochastic climate models paper, which I think is one of the best papers ever and is still highly cited even today. It has I just looked it up, it has an incredible amount of citations, almost as much as some key data papers, which is hard for a method paper. And so the idea is, and I think most of you in the audience know this idea well, is that slow climate components integrate weather variability. So basically you have dynamically generated chaotic fluctuations, and then these low climate components not only integrated in the sense of a red noise response, but beyond that get kicked into resonance possibly by it. So you can't only get red noise, you could get modes in response, modes of the ocean responding to atmospheric kicks, for example. And this moves from basically from weather variability to ocean involved red variability, and then you could get the ocean to trigger even longer variability that involves, for example, the large ice sheets. This is a key idea for the detection and attribution of climate change, because it says that climate generates low frequency variability even without forcing. And so we really need to be concerned not only about climate forcing, but also about climate variability, and that climate variability competes with the importance of external forcings. And the question of have greenhouse gases warmed the planet has to be expressed relative to this climate variability that we know occurs. This has been the key question in detection attribution all throughout, and is now also a key question in when we look at emergence. So which climate signals emerge from the weather variability locally, and impact, for example, also how important is climate change relative to variability we see anyway. And then he had written a second paper in 1979 that to detect climate change among weather noise, you have to use a signal processing approach. You have to use an approach where you don't look for the signal of greenhouse gases like a needle in a haystack in this huge multi-dimensional, multivariable climate data, but you have to come in with an expectation of what the signal looks like. So you have to have a fingerprint of what would you expect climate change to be like, and then being an excellent theoretical physicist, you actually don't have to use the fingerprint that you expect. You should really make this fingerprint, modify this fingerprint in a way that it is better suited to detect climate change, that it is less influenced by climate variability and more reflective of the force change. So that was the key idea. Both the 76 and 79 papers are hard work to read. I think when I started from mathematics and came into climate science, I think I spent the first few months of my time at Max Planck staring at Klaus' papers in what varied between total despair and enthusiasm. So it took me a while to digest them. And then a follow-on paper that will come in later is that in 1997, he wrote a paper that looks at what do you do if there's multiple external factors. It's basically just a simple expansion of the fingerprint idea into multiple fingerprints. An interesting point was that this whole idea, and I'm a bit nervous that I'm speaking to an empty room and I don't know if my mic works. Can anybody say that it still works?
Yes, it works.
Ah, good, yeah. Because my mic is not showing any lights, which is usually a bad sign. Okay, so all good ideas come when the time is ready. There had been the other two ideas came later than Klaus's. So there's no question about who won that race, but it is they are very different in approach. There's a Tom Bell paper, a beautiful Tom Bell paper in 1982 that talks about optimally averaging climate to arrive at the best way to detect climate change. So, and the idea was in that case not a fingerprint, but an average, that we are looking at globally average temperature, but we shouldn't just average it. We should weight it higher where the variability is lower. We should weight the tropics more than the high latitudes, for example. And that's a very beautiful and very nice, very readable paper. And then Jerry North in 1995 from Texas A&M wrote several papers framing it as optimal filtering of the climate signal out of climate noise. And one of the harder things and the last relic of Marx that I did in my job at Max Planck was I stared at these 3 papers for 3 months where I was visiting Texas A&M and also happened to encounter my husband, which is a totally different story, and found out that while they read incredibly different, they were mathematically totally identical. So they came up with the exact same idea, just from a very different approach. So what we now have is a method to detect climate change, which is basically a fingerprint method where you use the information about the shape of the expected signal and how to go for it. This is the only method slide. I just want to throw the method up once as it's phrased now. It's basically the observations Y are linearly composed of the fingerprints F, I. So fingerprints in response to greenhouse gases, for example, only fingerprints in response to aerosols, fingerprints in response to volcanism, etc. Each of which contains noise, something that had been recognized much later, and that's the total list square paper Allen and Stott in 2003. So the noise F came in by Allen and Stott. And so the sum of these fingerprints plus the observed noise, observed internal variability. And in the first paper and the first work I talk about, we just consider one single fingerprint of greenhouse gases. And in the second one, we look at multiple different impacts. And the optimal is basically at the bottom is the inverse, using the inverse noise covariance. You could mathematically think about this as using a metric that is better suited to separate out the things we want to separate out. In practice, this is a huge complication, and a lot of methodological enhancements in the recent time particularly have been around how to find this optimal fingerprint, how to do this better, because the inverse noise covariance matrix of a huge multidimensional climate metric is not easy to construct from data, because you need masses of data to estimate it, and if given that you have to invert it, means you have to be quite robust in your estimate. And there's a lot of papers about how to do this. There's been a lot of recent improvements. For example, I can't remember the term right now. Ridge regression and things like that. So there's a lot of methodological improvements that I'm totally not going to talk about because they're very technical, and there's a lot of devil buried in the detail of how to truncate. But so we had this fingerprint, and we had this fingerprint method. And so when I came as a postdoc to Max Planck Institute, we tried to estimate the first the fingerprint and then the optimal fingerprint, and then see what this how this was reflected in observation. So what we have a model simulation on the left, which is in this case the first UF of a very old model simulation, and then you have on the right hand side what the optimization does, what the multiplying this fingerprint by the inverse noise covariance does. So it does basically, if you compare the right to the left, you can see that the Arctic is less emphasized because it's very noisy. And so what you want to do with your method is de-emphasize Arctic warming because it is has a lower signal to noise ratio. You can see that the tropical warming is preserved. So that's something you really want to see. The North Atlantic cooling is emphasized very strongly, that is in part due to the limited truncation, but in part also maybe a real feature. But this is, if you use another model to optimize, you might get something slightly different. So you basically, instead of regressing your observations onto this left-hand pattern, which would be the straightforward approach and would be almost identical in outcome with just forming the global mean, you regress it onto this right-hand pattern, where you get a bit more emphasis on how much of the warming is in the tropics. And when you look at the patterns, you can immediately then probably preempt or expect that, for example, the early 20th century warming that peaks in the 1940s will be less emphasized in the right-hand pattern than in the left-hand pattern, because that was a very strong Arctic warming. And the result was this paper that we published in 1996 in Journal of Climate. It's a really bad plot. So this is the observations basically thrown onto that fingerprint and then you just plot its amplitude, and you can see the and what the observations here are trend patterns. This is a 30-year trend pattern of the surface air temperature data. Has lots of gaps. So where the gaps are, you ignore the data, which is a big, so you basically, constrain your fingerprint to where you actually have observed data. And then you plot a time series, which is the black, really hard to visit thingy. And it sticks out as a quite strong trend, a strong projection in the last data point, which is the trend that ends, I think, in 1995 or 1996. I can't actually remember. 1994. And so that's from the observations in black, and then the dashes is a model simulation, a very early one that Uli Kubasch ran, the early industrial, the experiment that started in 1935, and you can see that in that model run you expect a similar kind of increase a little bit later, as you see in the observations. And then we have estimated climate variability from observations by trying to subtract the greenhouse gas signal using the residual and see what does this tell us about how much 30-year trends project, random 30-year noise trends project onto that fingerprint just by chance, and then a control simulation with one model and then another model. And you can see that the GFDL one has a wider range, but the observations burst through both of them, which would lead us to say we have detected global warming at the time in 1996, which we also happily broadcasted in the paper. I was a bit concerned that you also had detected it in the 1940s, and that's something I'm gonna come back to much later in my talk. So we published this in Journal of Climate after the usual Nature rejection. So that was, and then Klaus did a press conference and disappeared to Sylt and was unreachable, which caused a lot of interesting complication at Max Planck Institute, and wound up with me on the local telly, which was an experience that is a totally different story. A problem that detection attribution has all along is what is climate variability. And so the paper talks about estimates, and that question had been arising in the literature actually earlier as well. So this is a spectrum from my paper, from which I learned at the time that it's very hard to say anything quantitative from spectra because they are so highly uncertain. So we have paleo data, observations, and different models in it, and the spectrum goes quite crazy and is nice and red, but very hard to say which are they really different here. At a similar time, Stauffer and Ron Stauffer and Suki Manabe had been plotting figures like this, this is here shown from a figure from a paper in 2001, but basically looking at the global mean temperature rise on the right-hand panel. So it's all on the right is the same global mean temperature rise, and looking at climate model variability. And this is three ancient models that none of which produces a rise as observed. All of which have different climate variability. So if now today at the time of CMIP6, you would plot this kind of thing, you would see the exact same picture, that climate models have really different climate variability, and this is something we still haven't come to grips with, I think. And we also have had a hard time rejecting any of the models as unrealistic in variability. But I think this is a big open question, and it's hard to get funding for because it's considered boring, but I think it's really interesting what is actually the climate variability. And that's a solution from paleo data from a paper by Andrew Schurer, where he basically plotted a 50-year trend from the instrumental data against 50-year trends from a whole lot of residuals from paleo data after taking out the forced signals. So subtracting the multimodal mean forced signal and then checking how much internal variability 50-year trends do you get. And you again get a very, you get in one sense a very robust result. In all cases, the instrumental trend is much larger than any of the model trends. And if you treat the model and data alike, and that's why the instrumental trend jiggles a little bit around, because these different 3 data sources are different, slightly different representations, but they are quite, the observations are really unusual. So the question, can we detect climate change, I think is really beyond all doubt. But on the other hand, what is climate variability? You can see that the different paleo data have different estimates, and this nice smooth Gaussian curve of the models, if you were to disentangle it, you would find that it is totally, the edges of the curve are dominated by high variability models and the center by low variability models. So it's basically throwing things together that are a bit questionable to throw together. So that was our paper in the 1990s, but we weren't the only ones looking at this problem. So Ben Santer had been at Max Planck before my time, and I moved on to Livermore when I came, and pretty much exactly at the same time as when I came, and had been looking at the detection of climate change quite a bit longer than me. There had been also papers by Dave Caroli and what they were looking at in this Nature paper that came out in 1996. Was the vertical structure of the atmosphere. And that, I think, was a really important paper that looked looked not for global warming at the surface, but in radiozones, which makes the time series a bit more uncertain and shorter, but also it captures an aspect of global warming caused by greenhouse gases that is very unique in some sense. It looks at the response to greenhouse gases here, for example, on the top left, which were very new simulations at the time. Some of them were time constant simulations, and they are not they're not exactly the same thing, but is there the change relative to a pre-industrial or a start state? And you can see that greenhouse gases in those simulations by Joyce Penner warm the entire troposphere and cool the stratosphere. Aerosols cool it, and then if you combine greenhouse gases and aerosols, you get a bit of a pattern that has the northern hemisphere warm less, and then you combine, and then ozone. I think this is the ozone fingerprint. Ozone cools the ozone loss in the stratosphere cools the upper atmosphere, and then you I think also in there is the ozone gain in the lower troposphere that slightly warms it. So if you combine all these things together, and he did in this paper, he did a very thorough analysis of how you could combine them differently using different models, then you get a pattern that looks like these two. If you have less aerosols, it looks more like this, and the radiozone data look like the bottom right diagram. And so it's so first of you see by eyeballing that this looks quite similar. If you at the way it's compared right now, you can't actually see this, but I think if you look carefully at the peak warming relative to the mid-tropical troposphere, you could at this point also spot that it doesn't. The models warm maybe the mid-troposphere a bit more compared to the north, compared to the southward, which is something that comes out a bit later as well. But basically, so they have this visual similarity, and then they do a pattern correlation statistics between anomalies of the all atmosphere on the left-hand side, so basically troposphere and stratosphere, and troposphere only. And what they see is this kind of increasing similarity, and they conclude that by some analysis with natural variability samples, that this again is cannot be expected by chance. So that what we see in the vertical structure of the atmosphere is an emerging similarity of the observations with what we expect from climate forecasting. So that came out in Nature, it reviewed very slowly, but came out and I think made a big impact. And that's showing the observations in a bit more detail and in a way that you can see maybe the stratosphere a bit more than in the plot before. Is something that Ben sent me lately for a comparison earlier on. And an ongoing issue that arose after this paper was that the mid-tropospheric temperatures in the observations are not as strong as you expect from the models. You can see it very nicely in that plot that in the models you would have a big bullseye around 200 hectopascal in the tropics. You expect from the moist adiabatic enhancement. So it's totally, it's very physically explainable, but the observations tend to show a bit less of that. And there have been a lot of discussions and analysis and data concerns so there has been an ongoing endless debate about the question to what extent this is a significant problem. And the solution seems to be, but probably more, some people in the audience know a lot more about that than me, that both ozone is leaking a bit more into the troposphere than expected from the model. So the ozone effect, and on the other hand, might also be something to do with convection. But basically in 1996, we had these two papers. We also had an earlier paper by Ben Santer that came out at a very similar, that was submitted at a very similar paper as my paper, that looked at the impact of aerosols on the spatial pattern of change, that also found a detectable change in surface temperature. So based on that, Ben Santer's led IPCC chapter on attribution of detection of climate change concluded that the balance of evidence suggests that human forcing, oops, and I've messed that sentence, caused a discernible influence on 20th century climate. I need to double check. This talk was a bit assembled in hurry. So they concluded that there was evidence that the observations contained the signal of climate change, and for Ben, all hell broke loose. And there is and if you want to know more about how all hell broke loose and how the people who created a huge amount of personal pain for Ben and a lot of doubt and problems, there's a nice paper by Naomi Oreskes that points out that some of the people were the same people who fought tooth and nail against legislations against tobacco being and showing that tobacco is dangerous to human health. And so it's basically to some extent hired guns. So so this was a very politically motivated character assassination for Ben, and really painful, and something he totally did not deserve, because all he did was do what he was told by the IPCC, which was to move the uncertainties from spread all over the chapter to one particular place that discussed uncertainties, if I remember the story correctly. And out of that was a huge conspiracy formed, and it was very painful to watch, and frightened, I think, all of us a little bit. The other thing that went on at the time and all during the time of these two papers were the method wars. That was a lot less visible, and I want to talk about them because it's a lesson in it for me, that you can get really hooked onto aspects of methodological detail that to everybody but the 5 people involved, or maybe 10 people involved, is totally angels dancing on a pinhead. But for us at the time was a very big battle. So the key proponent was Tom Wigley, who basically said that global mean warming is meaningless for attribution of climate change to causes. You may be able to detect it, but it doesn't tell you what caused the climate change. Anything can cause a global mean warming, and we really have to focus on the spatial pattern, and therefore we have to subtract the global mean if we want to detect global warming. We have to use regression. Instead of regression statistics, we have to use correlation without spatial mean warming. So I probably, and he signed my Nature rejection with exactly that argument. was strongly involved in the other papers that were going on. Meanwhile, by the way, he is actually a really interesting guy to talk to, and I really like him. I don't know what he's doing right now, but he did create a lot of complications by being very opinionated that you can not possibly do anything useful that includes the global mean. On the other hand, were Klaus and Jerry North, that's the optimal filtering guy, who basically was very, very strongly on the side that what happens in global warming is that we change the energy budget of the planet, and the key diagnostic for that change is global mean warming. And throwing that out is basically throwing out the strongest signal of warming, and we should definitely consider it. And we should not we should not remove the spatial mean. We should do regression with the mean included. And that sounds like, and there was this ferocious battle that you cannot use one or the other method, and people were upset with each other. And for me, this, and by now this has been completely resolved. We know that both methods have their strength. You want to know if the spatial pattern is similar. If you search for multiple patterns, in a multi-regression, immediately the pattern plays much more role than if you just use a single pattern. You have to always carefully look at what could be confounding your detection. So if you detect something significant, you have to think about what else could cause this. And so scientifically, this was a bit of a battle of a non-issue. It was also in doing IPCC, I learned that if you get consistent results with different methods that are used by different people with different rationales, that really strengthens your case. It's not dependent on one particular method. So in many ways, this was a wasted time, and I really regret the friendship with Ben that I missed in the years when we were both on different sides of that argument, which has now completely resumed. And I'm glad that we didn't that it didn't do long-term damage. But I wanted to tell this story because it's not the only time that I've seen this in my career. I've seen other young scientists being kind of bogged down in huge big battles that involve big egos, and I'm not meaning Klaus with that, because Klaus is a very unique person, that he's very confident but doesn't have to prove this to himself every 5 minutes. But there were some egos involved, and so that can really hurt the joy in science that a young scientist can have. And so if you spot that you're getting trained in one of those, run or kind of just do not engage with those battles. It's just it's not fun. So but in the end, it was resolved in a very oh, I wanted to first go back. Now let's go first to the resolvement. So it was resolved in a way by Klaus with his 1997 sorry, another typo, attribution paper, which says if we really want to figure out what caused climate change, we need to look at multiple signals, and we need to look at them explicitly. Ben, meanwhile, and that's a paper now from 2019, has pushed the atmosphere forward, the atmospheric work forward, and has recently written a really nice paper that looks at the history of detection and attribution. And I'm very, very proud to be a co-author. That looks at the evolution of the signal-to-noise ratio. So how much is the warming in the troposphere significantly larger than the internal variability, and he looks at that from 3 different data sets. So the various radiosonde data sets, and not radiosondes, there's 3 different satellite data sets, and there's a long story about who does the data sets with what ideas in mind, and what how they correct for very complicated satellite retrieval problems and merging satellites and so on. But all 3 data sets are now above the 5 sigma threshold, which is in physics a kind of a golden, a holy grail of detectability, like applied, for example, to the Higgs boson. So basically, global warming is blindingly obvious in the satellite measurements of the tropospheric temperature by now. I could quickly, I'm worried a bit that I'm running actually quite late. I could quickly go that the attribution method was then basically looking at 2 fingerprints. And we had this paper that we wrote in 1997. Klaus and Hans von Storch and myself and multiple other co-authors, where we basically say what the observations contain, and this is the point on the two-dimensional space of two patterns of the observations, is they contain a greenhouse gas fingerprint, which is global warming, and they contain some orthogonal aerosol fingerprints. So this is orthogonalized. Everything has been taken away that looks like greenhouse gases, and the thing that remains is basically a warm cooling in the north and mid latitudes. If this orthogonal fingerprint is less warming or more cooling in the mid latitudes, then the observations contain both. And Christian has raised his hand. Oh, that's probably telling me that I should get towards a close quite soon. And then we basically said the observations are within what we expect from greenhouse gases and aerosols, but outside greenhouse gases only and outside solar. And ever since we did this, and since we detected climate change, the planet has warmed a lot more, and as shown in this plot, we have had a lot more papers. Miles Allen has reframed the method into using, together with Sam and Ted, to use space-time patterns and fingerprints from simulations of the 20th century. We do a full multi-regression, and we use, so the orthogonalization has gone away. And we have lots more work accounting for lots more problems. We have also done this kind of intuitive attribution, where you compare the observations in black with model runs with and without greenhouse gases in red and blue, and have the IPCC has plotted it for in this way that you can see the observations are similar to models with both anthropogenic and natural forcings, but not natural only. We've done it all over the planet. We've done it also for ocean temperatures. That's the ocean heat content in the white panels, sea ice, and all regions seem to show an emerging signal of warming, with the expectation of Antarctic sea ice in this IPCC figure. I think it's from AR5. An interesting and important development in the way was that attribution has been reframed by Miles Allen into a signal estimation problem rather than a problem of detecting something, and that has been used. So basically, you not only estimate the magnitude of greenhouse gases to detect, to say they are detectable, but also to say what does this tell us about how much of the warming observed has been caused by greenhouse gases. And that has been, there's a complicated plot that shows this in AR4, but in the AR5 it was basically subsumed. Many studies doing this was subsumed into estimates of how does the observed warming in black compare to the warming caused by greenhouse gases in green. So based on these estimates from observations, more than the observed warming has been caused by greenhouse gases and has been offset by some non-greenhouse gas forcing in yellow. And if you bump both together, you get the anthropogenic total, which basically the orange bar is like the black bar. Pretty much all the warming has been caused by anthropogenic factors, with natural and internal variability doing almost nothing for 50-year timescale trends. And we have seen this has been applied so much across the climate system. We know so much more about how warming has happened. An interesting lesson I wanted to also to include for a minute is that was a figure that agitated us no end in AR4, even though this paper came out in AR5. But we knew that the observed ocean heat content was very similar in the Levitus data in trends to the models, but it had this variability that was enormous, and that really worried us at the time, thinking, whoa, we know nothing about ocean variability. What's going on here? This is no model does this. And it turned out in that case that it was a data artifact. So the Levitus data no longer have a big bump in the 1980s. But still, I think we don't really know ocean variability. We found it in rainfall. There was a paper that came out in 2007 looking at zonal rainfall trends being similar to what is expected from models, basically drying in the yellow regions and wettening in the green regions, and that is and the colored regions, the colored zonal bands are where the model expected and the observed change are consistent. And I'm gonna skip this, and I have, for my own mind, I've estimated that the early 20th century warming was something that satisfied me greatly. The 1940s warming was indeed caused by greenhouse gases, but also had a contribution by a lack of volcanic eruptions and a large internal variability contribution. And the last big methodological addition I just want to mention is Peter Stott's approach that he developed together with Miles Allen, that we can not only attribute long-term trends to causes, but we can also look at individual events and look at the risk ratio between what they have, of an event like that at the present time compared to pre-industrial. So that's another completely different form of attribution that's very widespread. And we are also, the community is grappling with and really struggling with the attribution of impacts to climate change and forcing. It's really important because it evaluates a very uncertain and difficult aspect of climate change. Has this impact been caused by this impact that I observed, this decrease in crop production, or would not being caused by, or this increased wintering rate of birds being caused by climate change? And so, for example, for the birds, you would worry about warming, not arming, winter warming versus bird food sales, which went up at the same time. So it creates a whole lot of new methodological problems, but it's also super important. And so what have we learned? I think the climate change detection attribution has strengthened by methodological advances. There's a lot more than I have been able to talk about. There is now causality methods coming along and event attribution. Nevertheless, the key result is robust since the mid-1990s. Human influence is the key driver of warming and is now found pervasive across the climate system. Climate variability flagged as a big uncertainty, and the scientific question is more important than the method, and scientific debates are really important and should be conducted in the peer-reviewed literature. But we should be careful about how we conduct these discussions. I think that's me. Should I just stop sharing, or how do we do this next?
Okay, thank you very much for this very nice talk. So if you have any questions, please put them into the Q&A, and I will read them to Gabi, and she can then answer them. So we already have a few questions. So the first question is by Francois Smith. Can you say a little more about the method optimal fingerprint? For example, what are the needed hypotheses? Do you assume Gaussianity in the model-specific noise properties?
Yes, so the method is framed for Gaussian noise. There are some discussions about doing this non-Gaussian. There has also been a new method that Francis Thiers is involved. I think that tries to get beyond that. But there are quite strong assumptions in optimal detection. One of them is that the noise behaves normal, which, if you worry about global scale warming, is not so tricky, because you look at an average of daily temperature over many regions. So so basically the property of normal distribution comes in, that the more you average, the more normal it gets. But if you go to precipitation and look at more regional aspects, you start to really have to be careful about that. You have to be careful about linearity, that your signals are linearly. There is a lot of work has been done to evaluate these hypotheses, but the more we get ambitious, the harder, the more we have to worry about this.
Okay, there's a question by Sabine Undorf. Hi Gabi, thank you for the very nice talk. Do you think regional DNA should become a climate service? And how do you feel about the use of DNA results for loss and damage?
Ooh, I think loss and damage is interesting to me, because intuitively I thought it would be incredibly hard to persuade a lawyer that this is actually, the models are strong enough and the data are strong enough. And I could see how, particularly for rainfall, how you could destroy the model projection in a combative court case. But I noticed that the lawyers are actually quite a bit more optimistic than we are. So I think for loss and damage, it's really interesting. Also for climate service, in the sense that we are trying to use it for a precursor project, the EUCP project, European Climate Prediction Project, that looks at observational constraints on the model projections, and DNA is one of the constraints, and Sabine has done some nice analysis on that. So I think it should be, it would be very useful for regional projections to think about the magnitude of changes. This is particularly interesting for precipitation, where sometimes you see a larger change in observations than in the models. It's also the case for aspects of heat, as Gert-Jan von Oldenburg has pointed out many times, that aspects of European heat are larger than what we expect. So we should really challenge our models by throwing the observations at them.
Okay, there's a question by Jenny Stavrakou. What is your opinion about the current trend in wanting to attribute single extreme weather events, for example, the European 2003 heat wave, to climate change in a quick operational way? What is the degree of confidence to such assessments given the large uncertainties, for example, aerosols?
That's a really interesting question. So initially I was quite nervous about the idea of rapid attribution. I think the papers that have come out of that and the studies that have come out have done both things, both a rapid attribution and then a more thorough analysis. I think it's a really interesting thing to do. I'm still a bit agnostic about the instantaneous attribution, but of course the media would like to know right after the flood if that has been enhanced by climate change. So it's more, it has more impact if you can do it quickly, but then the robustness is a big question. But there are some cases, I think, and the Met Office, I think in the UK works very strongly on that you have basically a database ready to go when an event rolls around, so that you can have the infrastructure to do this robustly very quickly. And also the World Weather Attribution has a machinery going that they can deploy really quickly. The US National Academies have written a report, one of these academy reports, on the question, is this a robust technique and should we really support this? And they have been very favorable. I was on the panel as a non-expert because I don't get any funding for event attribution. And I think it's a nice report that looks at both the difficulties and the benefits of doing that. So if you want to know more about it, that's a good report to download. 2016 or so, US National Academies.
There's a question by Serge Planton. Hi, Gabi. Can you say what is the state of the art concerning attribution of tropical cyclone change, wind intensity, and associated precipitation? Hi,
Serge. I saw your name on the participant list. I didn't say enough about the really big French effort on attribution as well, particularly. So there have been a few really important papers over time, including some of yours and then Aurelia's. The tropical cyclones is a really interesting problem. It's one where the variability is very hard to know in frequency, for example, from old data, because the data are not homogeneous. I think for tropical cyclone, there have been papers looking at the cyclogenesis regions, showing that the sea surface temperatures have warmed significantly due to human influences, and that this would strengthen cyclones. But cyclones individually are tricky. There have been event attribution studies that show that you get more rainfall in today's moister atmosphere with and more flooding with a tropical cyclone, more sea level also, more storm surge. But cyclones themselves are super tricky, and I think this is where a new idea, or it's not that new, an idea that we deploy attribution for mechanisms would need to come into play, that we look at the various components of what drives cyclone strength, for example, and attribute changes in the components that influence that, so that we target not a particular phenomenon, but a mechanism, and see if the observations support that this mechanism is important in data. So if a mechanism is important in models, we use the observations to evaluate if this is really the case.
Okay, thank you. There's one question by Pinhas Albert. What is your best estimate to anthropogenic versus natural factors in current global warming?
Oh, it's pretty much all. I mean, it depends on what you look at. Of course, if you look at yesterday's weather, then it's then the global warming is tiny compared to weather variability. But if you look at, for example, the trend since the 1950s or since pre-industrial, then it's basically all forced. I think there's no question in my mind that internal variability could generate trends like this, because if it could, we would have seen it in the proxy in the data of the last millennium. We would have seen much stronger trends than we do. We would so many things would have to happen for variability to be so large as to generate this variability. These trends that you look at something that is just hard to imagine. And then if it was the sun, then you would really see you would expect to see the 11-year cycle much stronger than you do. So you can estimate the 11-year cycle and it suggests that the 11-year cycle is marginally detectable at the surface with very strong detection mechanisms, but it's not at all as dominant as it would have to be a strong solar forcing. Also, proxy last millennium, we've just a study in the works right now, another one that basically with the high solar forcing estimates that are around for a low frequency solar forcing being very large, that's really hard to reconcile with the proxy data and our understanding of how last millennium temperatures evolved. So I think that's beyond doubt for me, and I'm fully behind the IPCC estimate. That's pretty much all the warming is all the long-term warming is anthropogenic with small uncertainties.
Yes, there's a question by Eric Quellström. Hi Gabi, thanks for a nice talk. You mentioned that natural variability needs to be better known, and you bring up paleo data in this context. Is this an area that receives too little interest? Are there new potential data sets that could be analyzed? Better harvesting of historical data?
Yeah, the historical data is a cool topic. What I wanted to say, by the way, when I said before IPCC estimate, I'm not talking about any upcoming IPCC reports. I don't know what they're concluding. I do know in some sense, but I don't. The paleo data. Yeah, there is a really fun project that I'm involved in that looks at, for example, measurements from the East India Company and looks at surface air temperature measured from ships much longer back in the past. So that is just one project, but there is a lot of data that are unused in logbooks and stuff, and some people are participating in digitizing them. So I think we have a lot of actual physical measurements that we are not making as much use as we could, and those would be really great for pinning down variability much better. Paleo data are really an exciting source of information. Tree data are the best bet for decadal variability, I think. But when you compare them to, for example, to instrumental data or to models, you have to be quite careful how you do this. You have to look at their spatial representativeness. Where are they taken? Do they reflect high latitude temperatures? Do they reflect growing season temperatures or annual temperatures, which can be quite different? Do they have a memory? And it looks like they might actually have a memory that if they don't, if you have a strong volcanic eruption, they might not go down, they might not respond as quickly as thermometers, but still show the damage in the year after. So you have to really spend some time trying to understand what they show for using them. So that makes it a particularly exciting problem to do, and there is a lot of work going on trying to, instead of compare climate model simulations of surface air temperature with and figuring out what the tree rings might possibly tell you about it, and instead go the other way, make synthetic tree rings from climate models and see if the variability you get is consistent. So there's a lot of interesting stuff going on.
Okay, thank you very much. That was the last question. So maybe we can stop here.